Okay, this week we're going to do 2.4 on Trig, and I'm going to break this into 3 videos, kind of give you an overview first of the things that we need to know and what the actual derivatives are, and then I'll do a proof of all 6 of them, and I'll break that into 2 videos. First video on the derivative of sine and cosine, and then we'll do the derivative of the other 4. The derivatives of sine and cosine are the trickiest ones to do. Now, here's the thing. Here's what you need to know. What you need to know is the derivatives. I'm not saying you shouldn't know where they come from and how the proofs work and all that, but here's what you're going to need to know practically. Practically, you need to know that the derivative of sine is cosine. The derivative, and again, I'm going to prove these, okay? So, stay with me here. But in the final analysis, this is what you need to know, right? The derivative of cosine is negative sine. What you'll notice is all the co-functions, cosine, cosecant, and cotangent, will be negative. That's something I just noticed when I was a kid, and it helps to remember that. There's kind of a pattern to them in terms of memorizing, because they're kind of a pain to memorize, okay? Y equals, the derivative of tangent is secant squared. The derivative of cosecant is negative cosecant cotangent. Remember I told you the co-functions are negative. Derivative of secant is secant tangent, and the derivative of cotangent is negative cosecant squared. So this is it, guys. I mean, in the final analysis, what do you need to know? You need to know this, okay? And there are some kind of things you do need to know beyond this in terms of why this comes about and all that, and we're going to talk about that a little bit. Now, right now I'm going to outline some of the things we need to know for the proof. Okay. Now, for the proof, there's going to be a couple limits that we haven't talked about that we need to know. Okay. We need to know that the sine of h over h is 1, and the limit is cosine h minus 1 over h is 0. Now, the actual proofs of these are a little long, and they actually use the squeeze theorem. It's on page 141 and 142, and the proof of this one is on page 143 in the textbook. You can also Google proof of this, and you can find the proof in a video. Khan does a really good job of this. I'm not a particular fan of this. It does require the squeeze theorem to prove. I will tell you this is one of Mr. Taylor's favorite proofs, is this one. But he's more into math than I am, I guess. But the proof of this is a little bit challenging because it requires the squeeze theorem. Then once you prove this one becomes almost like an offshoot of it. What I'm going to do is I want to kind of give you an intuitive reason for this being 1, okay? Let me just give you an intuitive reason for it being 1. Guys, if you look at the graph of y equals x, and then the graph of sine, now I'm adding tangent for the sake of discussion, okay? For the sake of discussion. Now remember, back up. What you really need to know is this, guys. Screenshot. It's also going to be used so much that you'll just have to memorize those, okay? You guys, but let me give you an intuitive idea of why that has to be 1. Notice that if you have y equals x, then you have the sine wave. Ignore the tangent. That's going to be something I'm going to throw in a second. Notice around 0, they're exactly the same. As you get closer and closer and closer to 0, it's kind of weird, right? When you get closer and closer to 0, they're really the same function. It's weird. You can actually say when x gets, let me put it in black here. Yes. So here's the weird thing, you guys. Here's the weird thing. As x gets closer and closer to 0, you can actually say these are true. Now keep in mind, they're not normally equal to each other, right? You can't normally say x is equal to sine x is equal to tangent x. Only around the origin, right around the origin. And you put in a graphing calculator and you can get a really good picture of that if you start zooming in. Matter of fact, at some point you won't see you only see one function if you zoom in far enough on the graphing calculator, which is what I normally would do in a non-pandemic situation. But what you want to get here is around the origin, oddly enough, x equals sine x equals tangent x. They're actually all equal to each other. It's kind of weird. So what we say is then, okay, this is not really the mathematical way of writing it. Mathematically, we say what's weird is the limit as x goes to 0 of x is equal to the limit of x goes to 0 sine x. So if these are equal to each other, then we know something divided by itself is 1, right? Because what I can actually do is I can actually get rid of, oh, so you can't see that, can you? I can actually get rid of the sign. I can throw it away. So now, oddly enough, sometimes they ask these questions in the AP exam, which I think is kind of weird. What would this be? And hopefully you figured it out, right? It's pretty obvious. It's going to be 7/3, isn't it? Because see, if this is true, the sign doesn't matter. I can throw it away. I can throw the sine and the tangent away around 0, right? Now you can't normally do that. It's got to be going to 0 to throw the sine away, right? Same thing here. This has got to be 4/9, right? Because I get closer and closer to 0, the tangent and the sine don't matter. They don't matter, and then of course the x's then cancel. And last but not least, around 0, the trig function doesn't matter, and you just get 5, 6. So, I kind of digressed. I got a little out of control there. So you guys, one of the things we're going to need for the proof is this. It's true only around the origin. It's got to be going to 0. It's got to be going to 0 there, right? And you can see it graphically that it has to be true. But the proof is available. And also, if you just put proof of the limit of h goes to 0, or you can use x. I think most people put x there. We're going to use h in our proof later on. That's why I used h there. But bottom line is these we're going to need. And then there's kind of a weird offshoot. They can sometimes ask this type of question on the AP exam. I don't ask it because I think it's kind of a silly question, because it seems weird to ask a question about something that we need to prove something that we really need. And back again, what do you really need to know? You need to know this. This is what you really, really need to know. Okay, you need to know these 6 derivatives. Now, a couple more things you need for the proof. Back in Trig, you learned the sum and difference formulas for sine and cosine. We're going to need those formulas for the proof. And I only mention it because if I don't mention it ahead of time, then you go, whoa, that's weird. Where did that come from? We haven't used that in a long time. Well, we're going to need this for the proof. And then, of course, last but not least, we're going to need the definition of the derivative for the proof, right? Because that's when you actually go to prove a derivative, you just use the definition to prove it, right? So again, a couple things for the proof that we're going to do for the next video. You need those things. You need this, and you need this. Now, just to end with today, let's do it as an example like 2.2. Let's just think about it for a second, okay? What could we do if we didn't know and we didn't feel like doing the proof? How else could I try to figure out what's going on? Draw the sine wave. Draw the sine wave, and then treat it like a 2.2 question, right? The one that you're going to have your quiz on, right, next week. Well, actually, might be before you actually watch this video. Depends on when you watch this video, right? I'm filming this a week before you're taking the test on this. Okay, remember how we do this? The derivative is 0 here, and the derivative is 0 here. So we drop the zeros down. Remember, that's the first of the 4 steps. Then the second thing is to do the positivity and negativity of this. And for the sake of discussion, I'm just going to extend the green one a little bit. In green here, I'm going to extend the sine wave just a little bit more on each side to kind of get the illustration here. So the second step is to do increasing, decreasing, right? So we can see that it's increasing, decreasing, increasing. So it's got to be up here. It's got to be down here. What am I doing? I'm not really doing a proof, but I'm doing a 2.2 question to kind of like, oh, well, what do I think the sine wave is going to look like? Okay. And then the third step is what we call the concavity step here, where we look at, oh, that's where it's going to be the most positive. And then this other point of concavity here, well, that's where it's going to be the most negative. And then this other point of concavity here, well, that's going to be the most positive. And then we can also talk about concave up and concave down. It's concave up here, so that means it's going to be increasing. It's concave down here, so that means it's got to be increasing. It's got to be decreasing. Then it's concave up here, so it's got to be increasing. And then here is decreasing. And then of course just connect the dots here. Just connect the dots. And surprise, 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 notice that we get the cosine wave. We get the cosine wave, don't we? Now that's not surprising because that's what it turns out to actually be. Now that's not really a proof, but I think students actually find this more palatable in terms of intellectual understanding than the actual proof, because sometimes the proof goes flying over people's heads. But we're going to do the proofs. Okay.